Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks or Geeks problem of the day, and today's problem is find all critical connections in the graph, and it is a hard level problem. So the problem says that we have been given the definition of critical connection. So critical connection is nothing, just basically a bridge, what we call in graph terms, and they have defined it as an edge which upon removal will make it impossible for certain nodes to reach each other through any path. So basically, if we remove that particular edge, the graph will become disconnected, or we cannot reach from certain edges to other certain edges. Right. Now we have been given the graph and we have to find all of those critical connections, and we have been given some formatting on the output such that, like forever, whenever we refer to an edge, we should always take the smaller element first and then take the bigger element to define an edge. And also the edge list, the final edge list of the bridges should be in sorted order itself as well. Now the problem basically boils down to finding bridges in a graph, and that is a very standard problem. We'll discuss it, and in case you need any help, so let me just tell you, you can search for this, you can search for bridges CP algorithms, right? You will find this particular blog post on the CP algorithms website. This is the blog post that I'll be discussing today. This says the algorithm, this is the algorithm, and if you want to have a look at the implementation, this is the exact code that I'll be using today, right? So that in case you need any reference to the original website, then you can refer to this particular website and you can read it yourself as well in case you are confused anytime later. Right, now we're just going to discuss whatever is being said in this particular blog, and I'm going to explain it in my own terms. So what is a bridge? We have already discussed the fundamental definition of a bridge. A bridge is any edge which, when removed, will disconnect the graph. Right. So for example, let us discuss in this particular graph what can be a bridge. If I remove this particular edge, will the graph be disconnected, or will the number of connected components increase? The answer is no. Similarly, for this bridge, the number of connected components will not increase. Similarly, for this particular edge, this edge as well as this edge, the number of connected components will still remain the same. Now, what if I remove this particular edge? If I remove this edge, the graph will now look like this, right? And you can clearly see the number of connected components has increased, and this is what a bridge is. If you remove this edge, the connected components should increase, or in the definition of what the problem statement says, there should be some edges, there should be some nodes which are not reachable from some other nodes now, right? For example, you cannot reach this particular node from any of these nodes now, right? Which was earlier possible. From any of these nodes you could have reached this particular node, right? This is what an alternative definition of edge is. Now our task is to figure out what are all the edges in the graph. So let me just give you an example. So let's say this is my tree or my graph, right? Let us consider this particular node as the starting node, and let us just traverse this particular tree in order traverse this graph in order to form a DFS tree. So what is a DFS tree? We are going to visit every node only once. So for example, I start from this particular node, I visit this particular node, then this particular node from this edge, and then this particular node, and then I traverse back. I do not traverse this particular edge because the node above it is already visited. Now I traverse back to the root node, and then I go here. So all the green edges are the edges which are traversed while the DFS and are a part of the DFS tree. So if I show you my DFS tree, it will look like this. This is my root node, this is one node, this is one node, this is one node, this is one node, right? So you can clearly see that this is a tree. Unlike the original problem that was a graph, this is a tree, and this represents all the nodes inside my graph as well. Just one edge is missing. Now why have I left that particular edge? Let me just give you some proper definition of what that particular edge is called. So all the green edges that I have marked and all the red edges that I have marked, these are two different kinds of edges. So let me just tell you that this green edge is known as a forward edge, and this red edge is known as a backward edge, right? and let me just move it a little bit. Right. Once we know this, what is the primary difference between a forward edge and a backward edge? You will always realize that the backward edge that we have can never be a bridge. Why is it so? Because this node is already visited. That means there is a path from this particular node to this node, right? The node that I am currently at. Now, if there is a path from this node to this node, that means even if I remove this edge, these two nodes will still remain connected. So there is no point removing this particular edge, right? Now, when a forward edge can be a bridge, we have already discussed that the backward edge can never be a bridge. Now, the only thing is that a forward edge can be a bridge. We have to determine the conditions under which a forward edge can be a bridge, right? So, you can clearly see when a forward edge can be a bridge. I'll have to figure out certain way. For example, this is my node and this is my child. If there is only one way to reach this particular child from this node, this is node, this is child, then this forward edge can be a bridge. Let me just reiterate this again. If there is only one way to reach this particular child node from this root node or from any other node, then this edge can be a bridge, right? Why is it so? You should realize that we disregarded this particular backward edge, that this cannot be a bridge, because there was primarily two ways to reach this particular node. That is the same definition that I am trying to apply here, that if this child node is only reachable through this particular node, then this edge has to be a bridge if there are no other ways to reach this particular node other than this particular parent node, right? Now, how can we figure out that there is exactly one way to reach this node? So, we are going to make use of something called in times, right? So, I'm just going to give you a quick dry run of what we are going to do on this particular graph that I have made. So, let me just make it a little better. So, this is our original graph. Now, I need two different arrays. So, just a second. This is my first array and this is going to be my second array. Right. Now, I have certain values in it. This is going to be my in time and this is going to be my low time, right? We are going to discuss what these denote, but let us just form the spaces first. 0, 1, 2, 3, 4, and let's say 0, 1, 2, 3 and 4, right? These are all the nodes that we have. So, I am going to have a timer. The concept of in time is, in time in this particular array is going to denote what is the time at which I entered my current node. So, let's say timer is initially equals to 0, right? So, I am just going to quickly write the in times of all the nodes. When I enter 0, right, the in time is going to be 0. When I enter 1, let's say after 0 I enter 1, so the in time is going to be 1. After 1 I enter 3, so the in time is going to be 2. After 3 I enter 4, so the in time is going to be 3, and then I traverse back, and then from 0 I enter 2, so its in time is going to be 4. So let me just quickly show you how a TFS is working. I started from the root node, this node. I just considered one node to be the root node. It's not necessary, you can start with any node. So I started from here, I moved here, that is why the in time is 1 here. Then from 1 I moved to 3, that is why the in time is 2 here. Then from 3 I moved to 4, that is why the in time is 3 here. And then I traverse back. So this node is visited, so I'm not going to traverse this particular edge. I will go back to this node, go back to this node, and then go back to 0. From 0, I'm going to visit 2, so the in time of 2 is going to be 4. Right. Now what the low time is denoting? I already said it multiple times that when there is another path to reach this particular child node other than this parent node, then this edge can never be a bridge, right? This edge has to be the only edge or the only way to reach this child from this node, that is the only case that this edge can be a bridge, right? So we want to find the same thing. Now let us set the low times, and this will help us to determine whether this is the only possible edge or not, right? So low time is going to denote the lowest ancestor or the lowest timing from which I can reach this particular node. We'll do a dry run and then you'll be able to understand it better. So let's say I start from 0. So the low time of 0 can be 0 only. Now I go to 1, right? So the low time of 1 is going to be 1 now, right? It is exactly going to be the equals to the in time initially, but we'll modify it later, right? Now when I come at 1, what I'm going to do is I'm going to go through all the different edges or all the different neighbor nodes. So 0 is the direct parent, I'm going to ignore it for now. Now 3 is not visited, so I'm going to visit 3, so I'm going to update its low time as well as 3. Now 4 low time is going to be 3 itself. Now again, why I did this? Because I am making the DFS calls first. When I come to 4, I am going to find out all the neighbors of 4. So the neighbor of 4 is 3 and 1. So 3 is the direct parent, I am going to ignore it. Now 1 is one of the ancestors of 4 from which 4 is reachable. So 1 is visited, it is not the direct parent. Now I am going to mark my low time of 4 as in time of 1. So I update this as low time of 4 is going to be in time of 1, which is 1. So by this low time array, I am trying to denote that 4 is reachable from this particular node, right? So not exactly node 1, but actually the in time of node 1, which is coincidentally to be 1 in this particular case. So do not confuse it with the node itself. This is not the node value here. This is the in time of the node from which this 4 is reachable, right? So this is basically what I am trying to denote from this low time array, that node 4 is reachable from a certain node whose in time was 1, right? So this is the low time of 4, denoting that this was reachable from this particular instant. Now I go back to 3. Since I have completed the DFS for 4, then I have to update the low time of for this particular 3 as well. So you see there is a difference. When this one node was visited, when this one node was already visited, I updated my low time of current node as minimum of low time of current node, comma in time of child, not exactly the child, but that node adjacent to it. Now when I have completed the DFS of 4, I come back to 3. I am going to update, after traversing 4, I am going to update the low time of node as minimum of low time of node, comma low time of child, right? So you see there is a difference between these two statements. In this particular statement, I am taking the in time of child. In this statement, I am taking the low time of child. Why this difference? Because here we can clearly see that 1, if we consider this particular graph, which is a DFS tree, we can clearly see that this node 1 is the ancestor of 4, right? That is why we take its in time. But now when we come back from DFS, this 4 is the child of 3 or is the successor of 3. That is why we take the low time of child, right? Once I update the low time of 3 as the low time of child, it is also going to be 1. So I remove this 2 from here. I'll have to use the eraser. So I remove this 2 from here, I update this 1. What this 1 is now denoting? This 1 here is denoting that node 3 is reachable from a node whose in time was 1, right? That basically means 3 is reachable from a node whose in time is 1. Now I come back to 2. Now I come back to 1. Now again I am going to update my in time of 1 as the low time of its children. So one of them is 3, one of them is 4. Both of them are equals to 1. So this is already 1. No change will occur in both of the arrays. Now I come back to 0. Now I am going to make a DFS call to this particular node. Since I have made a DFS call from here, right, this DFS is completed. Now I am going to update my low time of 0 as minimum of low time of 0, comma low time of child. So what is the low time of child? Low time of 1 is 1 and low time of 0 is already 0. I don't need to change it. I go back to 2, right? When I go to 2, what I'm going to do? I'm going to check what are the neighbors of 2, right? Initially the low time of 2 is also going to be 4, just as the end time, but now I'm going to update the low time of 2. So what I do, I see that this particular node 2 has no children other than this 0. So this is a direct parent, I am going to ignore it. When I come back to 0, now I am going to compare the low time of its children. So if low time of child is greater than in time of node, that they basically means that this child is is one of the successors, and this edge is going to be a bridge. So let me just explain this particular part. When low time of child is greater than my in time of node, then this particular edge is going to be a bridge. Why is it so? Because we have tried to minimize the low times of child. We have tried to match it to the ancestor, one of the ancestors, as close as possible or as early as possible. But if still the lower time of child is greater than my in time of node, that means there is no other way to reach this particular child other than this particular node, right? And that I have already discussed, if there is no other way than this particular edge, then this edge has to be a bridge, right? So this is the low time of child, this is the low time of this particular child. The low time of 1 is 1, the low time of 2 is 4, now the low time of 0 is 0. So both of them are greater than the in time of the current node. So in time of 0 is 0. Now I am going to mark both of these edges as bridges, right? So let me just quickly discuss what we did. We are traversing through the graph as a tree. So that basically means we are not going to visit any edge twice. We discussed in a theoretical manner that why backward edge can never be a bridge. Why? Because a backward edge is basically an edge connecting a node to one of its ancestors, right? That basically means one of that ancestor that has already been visited. So that means there is already a path from this ancestor to this particular node. Even if we remove this particular edge, it doesn't really make a difference. It doesn't make that particular ancestor and my current node disconnected, right? So backward edge can never be a bridge. Now, what are those forward edges that can be a bridge? Using the same idea that if a node is reachable from any one of the ancestors apart from my current direct parent, that means this edge cannot be a bridge. So that means if I have a node and I have a child, this should be the only edge from which this child is visitable or this child can be reached. That is the only case when this edge can be a bridge. Now we are trying to find out the same thing. This low array doesn't indicate anything special. In time array is very simple. It's just fixed and you know how to derive it. But this low time array is also very simple. It just defines what is the ancestor from which I can reach this particular node, right? So if there is some other way to reach this particular 4 other than this particular 3, that basically means this cannot be an edge or this cannot be a bridge. But if there is only one way to reach this particular 1, right, starting from this 0, then this basically means this is going to be a bridge, right? So if there are more than one paths, that edge cannot be a bridge. If there is only one path, that edge has to be a bridge. So what is this low time denoting? Low time of 4. Low time of 4 is 1. So low time of 4 is denoting what? Low time of 4 is denoting that it can be reached from certain node whose in time was 1, and that is this node 1. So when we come to 3, we see that 4 is also visitable from 1, 4 is also visitable from 3. There are two different paths. That means this edge cannot be a bridge. Similarly, at the last we see that this particular 1 and this particular 2 are only visitable if we start from 0. These are only visitable from these two edges. So this edges has to be bridges, right? This is what we try to do in this particular problem. Now let me just show you my code so that now you can understand this problem better. Again, if at any time later if you forget how to apply this particular algorithm, you can always visit CP algorithms. This is the same code at CP algorithms that I am going to discuss right now. The reason I have kept it the exact same so that you can relate to this particular code later on, right, after reading that particular blog as well. Now I have initialized my visited array, my in time array and my low time array and my timer, right? So you see all the values are not visited, all the values are 0 here and all the timers are 0 here as well. Now I just have So I'll have to take this. So you see, I'm just making a simple for loop. If this particular node is not visited, I'm going to start a DFS from here. At the end, I'm just sorting the answer and just returning the answer. Let us see what interesting is happening inside my DFS function. So you can clearly see that I mark my visited as true. I mark my in time and low time of node as timer, and I post increment the timer value. Now I just traverse through the adjacency list. If my child is my direct parent, that means this is just a direct parent. I have to continue. I don't want to use this particular edge. Now if visited child, that means my current child is visited, that means this is going to be a back edge, right? This edge is going to lead to one of the ancestors of my current node. That is why I mark my low of node as minimum of low of node comma in time of child, right? This is not exactly the child, this is one of the ancestors of my current node. That is why this node was visited before my current node, right? So now if this node is not visited, I'm going to visit it, and that basically means the next node is actually my child. It is not one of my ancestors now, it is going to be my actual child, and then I'm going to update my low of node as minimum of low of node comma low of child, right? Now if my low of child is greater than t in of node, that means in time of node, I'm going to push back this particular pair or this particular edge as an answer. I'm going to take the minimum of node child as the first argument and maximum of node child as the second argument. So you see, in this case, when the child was already visited, this clearly showed that this is one of my ancestors. That means this node was already visited. That is why I didn't even check for the condition that this can be a edge or a bridge, right? I just directly updated my low of node as minimum of low of node comma in time of child, and this is one of the reasons I took here in time of child, because this is not actually the child. This is, let me just write it, actually this is actually a what do we say, parent, or I'm not getting the proper term, uh, actually a grandparent, right? Let me just use this term for now. So this basically means that this ancestors, yeah, so I got the correct term, this is one of the ancestors, right? So this basically, if the child has been visited, that means this particular child node which I am referring to as child is actually one of the ancestors. If it is one of the ancestors, I have to use the in time of that particular ancestor, and this basically means this edge is going to be a back edge and this can never be a bridge. Only when this is my actual child in the DFS tree, I'm going to visit this child. I'm going to mark my low of node as minimum of low of node comma low of child, since this is the actual child now, and I'm going to consider the fact that this can be a bridge, and I can check it with this particular condition. If low of child is greater than t in f node, that means this is the only edge from which I can visit this particular child and there is no other edges, right? So this is going to be my bridge and I push it into my answer. So this was all about this particular problem. Let me just quickly submit this and show you that this particular code works and the solution is absolutely correct. So this is actually an ancestor, right? So you see this passes all the test cases and the solution is absolutely correct. I hope that you guys were able to understand the problem and the solution. If you guessed it, then consider dropping a like on this video and don't forget to share thoughts in the comments, because your engagement with this video really helps the YouTube algorithm to understand that this video is actually helpful for you and it will be able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.